Hi, welcome to National Math and Science Initiative's Professional Development Video Lecture Series for AP Physics 2 teachers. This is Module 3, Magnetism, Part A, an overview of how magnetism appears on the AP Physics 2 exam. My name is John Frensley. I teach at Prosper High School in Prosper, Texas. I have a Facebook page titled Frensley Physics. You can search Frensley Physics Facebook on Google and it's the first thing that comes up. You and your students are invited, to make a resource out of Frensley Physics. If you like Frensley Physics on Facebook, then you'll get an example question in your news feed every weekday and solutions for the entire week on Saturday. That's for you and for your students. So, a resource for you. All right. Here's the focus. The focus of magnetism is really in three places. One, understanding how magnetic field is even created. How do bar magnets create magnetic field? How do straight line wires create magnetic field? How do solenoids create magnetic field? How is magnetic field created? And what's the relationship between, say, the current in the wire and the distance from the wire, the strength of magnetic field created? The directions of magnetic field created. Magnetic force on magnets, on moving charges, on current-carrying wires. So we create the magnetic field. Now the magnetic field's got to exert force on something. And then third of all, electromagnetic induction. How can magnetic fields be used to create electricity? If electricity creates magnetism, how does magnetism create electricity? That's about the scope of the magnetism in AP Physics 2. We have looked at all of the AP Physics 2 exam items from all topics, and we have counted basically the number of equivalent points that land in all the different topics, the number of total points of all published AP Physics 2 exam items for electrostatics. The total number of points that have been given to circuits, into magnetism, to optics, and things like that. So it turns out that only 8% of all the points of all the published exam items, that includes behind the audit wall and includes multiple choice and free response, only 8% deal with the scope of this topic on magnetism. So what does that mean? That means that you might want to consider spending 8% of your time on magnetism. Now, if you're planning a 30-week year, 30 solid weeks of teaching, not any little dinky weeks, not the week that you lose to homecoming or any of that hogwash, you probably need to be teaching magnetism at least 2.5 weeks. But be careful. There's a couple of things you got to consider here. Number one, 2.5 weeks is not enough time to really master magnetism. Just going to tell you that right now. Okay, number two. On the other hand, you can easily get bogged down in magnetism and it turns into a 4 or 5 week affair. Don't let that be you. That's wasted time, in my opinion. So what I would say is, I would say this. If you watched Module 2 on circuits and you did a really solid job of teaching your circuits to your students when they were in AP Physics 1, you can take some time from circuits and pay it to other topics that you think students struggle with or you think show up more often on the exam. For me, I spend less than 6 weeks, even though that's the recommended amount of time, on circuits, because I do what I would consider to be a good job of teaching circuits in AP Physics 1. That being said, what I would do is I would not spend more than 3.5 weeks on magnetism. So for me, it's 3.5 weeks on magnetism and then I give some of the other time to atomic and nuclear physics, which is showing up more on the AP Physics 2 exam than I thought it would. Okay, it's critical that your students understand the difference between gravitational, electric, and magnetic fields. Gravitational field, it's a field caused by the presence of mass, exerts a force on other masses within the field region. Electric field is caused by charges, created by charge, and exerts force on other charges in the field region. Magnetic field is created by moving charges and exerts force on other moving charges. Well, what about a bar magnet? What about iron? What about ferromagnetic materials? Well, the moving charges are the electrons that are in little orbits in the iron atom, and those moving charges, as they circle, they are the moving charges that create and are affected by magnetic fields. Well, why doesn't that happen for other materials, Mr. Frensley? Well, this is the part where you're probably going to start wandering into chemistry, so be careful. But the bottom line is that for ferromagnetic materials, you have many electrons that are orbiting in one direction, that have a spin in one direction, but you don't have other electrons orbiting the other direction. For most other elements, for every electron that spins one way, you have an electron spinning the other way, and those magnetic effects cancel out. But not for iron, nickel, cobalt, and some extremely serious magnets like neodymium. Okay. It's also important that students know magnetic interactions can only take place in a three-dimensional world. We can't do magnetism in just two dimensions. We have to be able to talk about up and down, left and right, and into and out of the page. So because magnetism only takes place in three dimensions, we have to indicate arrows pointing into the page with a cross and arrows pointing out of the page with a dot. Make sure they understand that, that convention. Magnetism wants, I know that some of you out there hate it when people personify physics, deal with it. Magnetism wants all things to be perpendicular. So what that means is that magnetic fields will not exert any kind of force on charges that move parallel to the field direction. If the charge moves parallel to the field direction, there will be no force. However, if the charge moves with any perpendicular component to the field region, then the magnetic force will be perpendicular to both the field and the motion of the charges. Very important to know. So it's important that students understand that basics. Here they come, topics that are overrepresented. How do you say overrepresented for something that shows up only 8% of the time? Here's what I tell you. This is what I want to focus on when I do magnetism with my students. Okay, you know what? I'm not going to go through this three-segment naming convention. If you're watching this this module for the first time, like this is your first module you're seeing, I'm going to ask you to go back to video A of electrostatics or video A of circuits, where I explain how I name questions. So what you'll see in a moment is you're going to see all these questions written as serial numbers for the questions. How do you understand what those are? Go see those other videos, will you? Okay, here we go. Bar magnets are showing up a lot on AP Physics 2, a lot more than than AP Physics B, the old exam, and more often than on Physics C, Electricity Magnetism. So if you teach Physics CE Mag, you might blow off bar magnets. They're showing up on Physics 2. They show up in the course description, multiple choice number 10. The practice exam, we had 2 bar magnets on practice exam. That was behind the audit wall. And this interesting one from the practice exam behind the audit wall that was just released like a couple of weeks ago as of the time of this recording. And then there's a couple of electricity and magnetism questions from Physics C behind the audit wall that also use bar magnets. I would encourage you to have a look at them. They don't involve calculus, or else I wouldn't recommend them, but I think they're good for class discussion, helping students understand bar magnets. Students have to understand point charges in a magnetic field. If you're given the velocity of the charge and the sign of the charge and the direction of the field, what direction is the magnetic force? Or they could be given the field direction of the force and the sign of the charge, what's the direction of the velocity or something like that. So in other words, your right-hand rule stuff. Your right-hand rule stuff for me, my right-hand rule is motion of the charge, magnetic field, and force, but you can do it however you want. Okay, you'll see that it's shown up a little bit on AP Physics 2. The motion of a point charge in a magnetic field showed up on 2 entire free responses. So if you see that magnetism is 8% and you're like, maybe I can skimp on it, you're going to be sad if one of the 4 free responses has magnetism on it. So I would not skimp on magnetism, but just don't get bogged down in it. And then we have some multiple choices. Basically a multiple choice kind of about every year. To help you with more of these, since P2 has not been around for very long, the kind of questions that are kind of like the ones on P2 are those here with that say C, electricity and magnetism. One of the things that has not yet shown up on P2, but I feel like they could do it, is this. You have a charge moving through both an electric and a magnetic field. Some of you know where this is going, right? Where you have both an electric and a magnetic field in the same region of space. what has to be true in order for the charge to go through both fields without feeling a net force? Well, that's these three right here, these three that I separated out. So please feel free to peruse those. I would strongly encourage you to teach that idea. We don't know when it's going to show up on Physics 2. We want to give the students a chance at it, right? Circular motion. There's several of these talk about circular motion, these two especially. They talk about the motion in a circle of the charge. Okay, I'm going to tell you right now, calculating the magnetic field that a wire creates really hasn't shown up on Physics 2 yet. Talking about the direction that the magnetic field circles around the wire has not shown up on Physics 2 yet. However, what I'm going to tell you is that it is important for the next slide I'm about to put up here that students understand the right-hand rule for magnetic fields circling around a wire, and that they understand how the distance decreases, or they understand the equation, it's B equals mu naught I over 2 pi r. It's on their formula chart, so you better teach it to them, how the magnetic field decreases with distance from a wire. So, you don't see a lot of, this is the only time that AP Physics 2 is asked about just the magnetic field from, and that one has 4 wires on it. Here's some other examples of questions from C Electricity and Magnetism that are of the type that I could imagine being on P2. What's all these then, John, or Frensley, whichever one you want to call me? What are all these? Well, this is what P2 likes to do. They like to show a wire carrying current and a charge next to the wire, moving with or against or perpendicular to the wire, and they'll say, here's the direction of the current in the wire, here's the charge and motion of the magnetic of the charge particle, what's the direction of the magnetic force on the charged particle? In other words, what they'll do is, what the student has to do is they have to use the right-hand rule to figure out the direction of the magnetic field at the location of the charged particle. And then they need to do another step where they do a right-hand rule to figure out the direction of the magnetic force on the charged particle. That's everything from this break onward, is all questions where a wire forces a moving charge. I would strongly encourage you to look at them, because boy, that's showing up a lot on the AP Physics 2 exam. Dang. Okay. There's really not been a lot of Faraday, Lenz's law, electromagnetic induction. Really hasn't shown up a lot on P2. So if you're an I'm going to pick my battles type of person, this may be one that you pick to skip. I would not recommend it, but I would also, it depends on how much time you have left in the year and how you're strategically presenting topics. For AP Physics 2, we've only seen across 3 released exams. So the 3 released exams, four released multiple choices. The practice, what do we call it? The practice behind the audit wall that was never used as a operational exam. I call it the prototype. The prototype exam, which didn't even have that on it at all. Let's see. The 2015, 2016, 2017 released multiple choices behind the audit wall. You'll see that EMF induced specifically by a motion has appeared once on each of the real exams, even one time as a multi-mark. So what am I going to give you? I'm giving you these electricity and magnetism multiple choices and these old Physics B free responses as example problems you can use with your kids to help them practice this idea. And some electricity and magnetism Physics C free responses as well. It's not shown up yet. I cannot promise that it will never show up. The formulas are on the formula chart. Finding EMF or creating EMF by changing the flux through the loop, turning the loop, changing the size of the loop, changing the strength of the field. Hasn't shown up yet, doesn't mean it won't. I think it will. So what are you going to do? I would expose your students to these really good C electricity and magnetism questions. And if there was going to be a free response on this topic on the AP Physics 2 exam, that free response would probably look like this B question from 1982. Go dig it up. Look at it. It's important. Okay, so here we go. Don't forget to teach your students Lenz's law, the one where you figure out whether it's a clockwise or counterclockwise induced current. But once again, if you're picking your battles, it may be one to pick. So what are you going to do for hands-on, on paper, or class discussion, that kind of thing? I'm going to show you some hands-on activities in module, or in video part B of this module. I'm going to make a TV be distorted with magnets, and then we're going to talk about how you can use that to teach your kids. Yeah, it's cool, but the question is, don't just show your kids cool stuff. Show them cool stuff, but don't just do that. Make them learn from it and explain it, right? Compass near a wire demonstration. How we can use magnetism to lift up a wire or push down a wire. How a magnet can induce current. That's part B. That's all demonstration stuff. Or for part C of this module, we're going to do a few labs. I call it the magnetic field inside the box lab. It's a lab where you're going to find and measure the magnetic field inside of the box using a current carrying wire. And then another one I call Earth's magnetic field lab in part C. These labs are pretty ornate. They're pretty serious business. They require very large setups, and I only have one setup for the entire class. The entire class does it together as one lab group. On paper, doing right-hand rules, doing the calculations, plugging into the equations, and that kind of thing. And class discussion might be discussing how can we use the right-hand rule, how can we do it, Lenz's law, that kind of thing. What would happen to the radius of the circular motion if we doubled the magnetic field? Or what if instead of a proton, it was 2 protons and 2 neutrons stuck together that were traveling with the same speed through the magnetic field? Those kind of conceptual or semi-quantitative, where you double or half or whatever a quantity, have those as class discussion. All right, so I'm going to see you next time, part B. We're going to see how we can make some good demonstrations and class discussion pieces with magnetism. Then part C, we're going to see some labs. Be there or be nowhere.